Good morning. My name is Dan Davidson. I represent the Illinois Soybean Association. I want to take a moment to thank you and welcome you for attending today's webinar in sulfur's role in soybean production, being presented by Wesley Haun. This webinar is one of a series we do throughout the year on the ILSOY Advisor website. Just a few logistics. We're starting right on the hour at 10 a.m. Central Time, and we'll be done at 11 a.m. Central Time, so we watch that closely. You can go ahead and submit online any questions you want to ask, and we will take those and collect them and review them at the end of the session. As a CCA, or if you are a CCA when you're registered, you put in your CCA number and you will be given a credit for participating if you happen to stay throughout the whole session. If you're listening to the recording online, you can log into your CCA account to American Side of Agronomy, and then you can self-apply for a credit for this event. One credit in nutrient management has been granted by the American Side of Agronomy. So, the webinar today is on sulfur's role in soybean production, and our presenter is Wesley Haun from H.J. Baker. Wesley is an agronomist with the company in the Crop Performance Division. His activities include coordinating soil fertility and crop nutrition research with various research organizations in the U.S. and internationally. He leads seminars and webinars such as this, publishes technical information and bulletins and newsletters on the applications of sulfur, bentonite, the product, as well as micronutrients. We're grateful. I want to thank Wesley for making this presentation today, and we look forward to hearing all about sulfur in soybeans and why it's important that we start paying more attention to this. Wesley, I'm going to turn it over to you.
Well, thank you, Daniel. I am honored by your invitation to participate in the Illinois Soybean Association's webinar series. And today I would like to discuss sulfur's role in soybean production. And I like to use Liebig's law of minimum and the stave barrel concept. You know, when you got several broken staves there, the maximum amount of water that barrel is going to retain is to the lowest stave. So I like to compare this to soil fertility standpoint is, you know, we want to minimize or reduce the amount of yield limiting factors that influence crop production. So first we focus on the most yield limiting one, in this case the lowest stave being sulfur. We focus on that and eliminate that one, so we bring, or actually put that stave all the way to its maximum height, and then we focus on the next lowest stave, in this case being a manganese, and once we fine-tune that one and get it back up to maximum potential, then you continue to focus on the next yield limiting factor until we've got them all maximized out, so that soil fertility cation exchange complex can maximize the amount of nutrients that the plants have access to. Sulfur is a secondary nutrient that's essential for plant growth. In some crops, when you do a plant tissue analysis, you will find that there are similar amounts of sulfur as there is phosphorus in that plant. And sulfur is critical in a number of plant metabolic functions, including the component of amino acids, vitamins, and enzymes, as well as part of photosynthesis and seed formation. So sulfur in plant nutrition, we know from research that sulfur deficiency will result in yield reductions and also reduce grain quality. And by reducing grain quality, we're adversely affecting the amino acids due to the lack of sulfur. And then if you don't have the full amount of amino acid synthesis taking place, then we're going to lower the protein content of the grain as well. Sulfur is a necessary component of two amino acids, particularly methionine and cysteine. Sulfur is also involved in the structure and the function of a number of enzymes within the plant. and metabolism and physiology within that plant, or all that plant here, is dependent upon a number of sulfur compounds. So here again, sulfur is important, and we as agronomists find continuous challenges trying to evaluate plant available soil sulfate and consistently correlate soil additions to a predictable yield response. A number of factors influence this, and we will discuss some of those going forward in this presentation. There are some factors that influence soil sulfur availability. Those include low organic matter. Coarse textured soils tend to be sandy. Sandy soils generally are well drained, and a low soil pH. So any one or combination of these factors tend to lead to a sulfur deficiency. Now, in recent years, we have noticed that even beyond these situations, even in soils that contain higher organic matter, upwards of 5–6%, have displayed some sulfur deficiencies. So that means we need to focus on fine-tuning our soil fertility evaluations. So what are some of the sources of sulfur? And we'll start with the natural sources. Organic matter is the largest pool of sulfur. As organic matter decomposes, sulfur compounds are released and can be taken up by the plant. Atmospheric sulfur, both the sulfates as well as some sulfur dioxide. Sulfates being removed from the atmosphere with precipitation, and the gaseous form being sulfur dioxide can be taken up by the plants through the foliage. And then as soil minerals weather, some sulfur compounds are released through the mineralization process and oxidation process and available for plants to take up. Another group of sulfur sources are the sulfates that many of you are very familiar with. Those include ammonium sulfate, potassium sulfate, ammonium thiosulfate, calcium sulfate, as well as single superphosphate. And there are other sources of sulfates as well, to a minor degree, that can provide readily available sulfate to the plants. Now, these are all water soluble, and once they are applied, dissolved in soil water, they are immediately available for plant uptake. And then the other group of sulfur sources are the elemental sulfur. Pure elemental sulfur is 99.5% sulfur. Then you have the sulfur bentonite products, such as the ones we manufacture, with both 90 and 85% sulfur. There are some correlations between sulfur and nitrogen. Nitrogen is a primary nutrient, sulfur is a secondary nutrient, and all the 16 essential nutrients, these are the only two nutrients that require microbial activity to convert some forms of those compounds into a plant available form. And when we add these microbial factors, it makes it much more difficult to get our arms around managing both of these elements to maximize plant availability and to minimize loss from the fields. So to review briefly the sulphur cycle, starting with the plant at the upper left-hand corner, once that plant dies and the residue goes back to the soil, that residue is inacted upon by bacteria, and through the decomposition process is converted to hydrogen sulfide gas. If the residue is on the surface and the transformation takes place on the surface, obviously gas is going to dissipate into the atmosphere and be lost. If this is within the soil, then that can be converted to other forms of sulfide, whether it be iron, manganese, or zinc. Or the hydrogen sulfide can be converted directly to elemental sulfur. And then the elemental sulfur then is acted on by aerobic bacteria, primarily thiobacillus, and converted to sulfate. Sulfate is the form that can be taken up by the plant. And if there's excess sulfate over and beyond what the plants can take up, and you have excess rainfall or irrigation, that sulfate is subject to leaching, as it is a natively charged anion. Then if you have an extended period of time of saturated soil conditions or clay conditions, some of that sulfate can convert back to hydrogen sulfide gas. Now, the top part of that nitrogen cycle is considered the mineralization process, and the bottom side of that, where you convert the elemental sulfur to sulfate, is considered the oxidation process. Those processes are very similar to the nitrogen mineralization process as well, and this is driven by 5 factors. The temperature, soil temperature needs to be in that 70 to 95 degrees Fahrenheit for optimum microbial activity to take place. Now, the microbes will start becoming active even down at, say, 55, 60 degrees, and then as the temperature rises, they become more active, and you get the faster conversion as the temperature rises into the optimum range. Then soil moisture. Optimum soil moisture is about just slightly below field capacity based upon a given soil type. Here again, the microbes require this moisture in conjunction with the temperature to maximize their activity. We need good aeration within that rooting zone, as the primary bacteria that converts elemental sulfur to sulfate, it requires oxygen. And then microbial activity is a function of the population. The higher the population of microbes, the faster that conversion process takes place. And then certainly, last but not least, is the sulfur particle size. The smaller that particle size, the greater the surface area, which provides greater points of attachment by the microbes to feed upon that sulfur to convert it to sulfate. Now, just looking at some of the chemistry involved here from the sulfur cycle. Remember, at the top of the cycle is hydrogen sulfide. We take that, combine that with some oxygen and presence of bacteria, we get to water and elemental sulfur. That elemental sulfur then, presence of oxygen and water with bacteria, produces sulfuric acid. The sulfuric acid then reacts with any calcium carbonate that's present in the soil, converts that to calcium sulfate plus carbonic acid. Carbonic acid is a weak acid. It will dissociate into water and carbon dioxide. Now, the important part of this oxidation process is the sulfuric acid that's produced. When this is generated and released into the soil, hydrogens are kicked off, and then we can lower the pH by adding these extra hydrogens. Okay? Now, a question I often receive is, to what extent will this lower the pH? Well, that's a function of a number of factors, including the soil type, soil texture, the population of the microbes, the amount of sulfur that's added, the crop you're working with. So when you're applying sulfur at the crop nutrition rates of 20 to 35 pounds per acre, there'll be a minimum amount of activity toward the reduction of pH as compared when you apply a much higher amount, and then you see a greater amount of activity toward reduction in pH. But there again, a number of factors come into play, and we need more specific information to answer that question more directly. Now, the oxidation of elemental sulfur, and this is one that most people are not as familiar with as compared to the sulfate forms. So with the sulfur bentonite products, we have in this case, a 90% elemental sulfur, adding a 10% dispersing agent. In our case, it's bentonite clay. And when we add 1 drop of water to that pastille, that bentonite clay that's present absorbs the moisture, causes that granular pastille to swell and fracture and break apart into fine powder-sized particles. And it's these small particles that the microbes can attach to and convert more readily. Okay, here's some photos of the products and more color, and showing the fracturing and breaking apart in the fine particles that are generated in that process. Soil pH regulates plant nutrient availability. It influences microbial population. Here again, with the oxidation of sulfur to sulfate, it's a bacteria, and generally you see greater activity when that pH is greater than 6.5. When the soil pH drops below 6.5, generally fungi tends to become the dominant population. And then with legumes such as soybeans, nitrogen fixation is very important. So we want that pH to be above 6.0 for some legumes, but for soybeans, we like to see that more at 6.8 so that we maximize the microbial activity there in the nitrogen fixation process as well. Many of you have seen this chart as it relates to soil pH and the availability of nutrients. On the x-axis, we have a portion of the pH scale. And what we do is you look across these different pH ranges to look at the maximum amount of width, which indicates the greatest availability of all the nutrients. When you look across all the nutrients, generally the widest range of those generally falls in that between that 6 and 7.0 pH scale. Now, sulfur uptake by plants, as I indicated earlier, it's in the form of sulfate, and the uptake process itself is not pH sensitive, and plants are relatively insensitive to high concentrations of sulfate in the soil, particularly as we work with crops that are grown in the Midwest relating to corn and soybeans. There are some specialty crops that have exceptions to this. Here's a chart showing sulfur uptake by soybeans with yield in the left column, starting at, say, 40 bushels to the acre. We take up approximately 0.36 pounds of sulfate per bushel. That equates to about 15 pounds per acre of sulfate of crop uptake. And then the crop removal at harvest is approximately half of that at 7 pounds per acre. And notice if you go down to 80 bushels per acre, we essentially doubled the amount of crop uptake and we had doubled the amount of crop removal. But still, there's only about half being the difference between crop removal and crop uptake. And oftentimes I get the question is, well, what about the difference there between uptake and removal, since we're not taking off 7 pounds or 15 pounds there, as that residue from these soybeans, as it breaks down, is that sulfur available? Well, yes, it is, but we don't have a good research yet to document in consistency as the amount of sulfate that's going to be available from that residue in the decomposition process. In a similar situation with corn, for example, many of you are growing corn and soybeans in rotation. For example, for 150 bushel corn, you need about 23 pounds that's taken up by the crop, and about 12 pounds of sulfate that's actually removed. So here again, corn residue does not break down as fast as the soybean residue. So here again, that differential is not predictable as to being available for the next crop. Here again, as we look at this nutrient uptake, efficient nutrient uptake requires interaction at the root soil interface. This is a microscopic zone called the rhizosphere. Within that rhizosphere are mycorrhiza fungi. These fungi actually interact and enhance the availability and the uptake of various nutrients. And the nutrient uptake process can be either active or passive. Here again, active uptake is where the plant actually has to exert energy and releases a protein carrier that attaches to the nutrients and then move it across a active membrane. Whereas the passive process does not require energy from the plant, but here again it has to move across a concentrating gradient as well, but I like to look at it as going downstream rather than upstream. And here again, this is the way sulfur is taken up, and through mass flow with the sulfate ion being negatively charged, it moves with the soil water across the root mass and the rooting zone. So here again, we're picking up on mass flow, water movement to move that sulfate to the plant for uptake. Now, as plants enter into that rapid growth phase in mid part of the growing season, the number of roots increase significantly as that plant demand for nutrient and water increases dramatically. So any restrictions at this time will dramatically reduce the plant's ability to take up nutrients, whether that be compaction, insect feeding, wet soils, cool soils, and etc. So here again is to minimize the amount of restrictions so that root mass can grow and take up the maximum amount of nutrients that crop needs. The plant rooting volume is the primary influence on nutrient uptake and water uptake as well. So any condition that minimizes that growth will adversely influence the seed yield at the end of the growing season. Oftentimes I receive the question, well, if I do have some restrictions I can't manage, can I ban or apply these nutrients in the furrow to increase the availability of the nutrients? And yes, you can, but actually the uptake may not increase just because you have an increased availability. Just a word of caution though, as far as in-furrow treatments, I would not encourage any ammonium sulfate, any of the sulfates that have ammonium in it. I would not put in furrow because the salt index is much higher as compared to the sulfur bentonite products. You can ban to the side as long as you have a soil zone to buffer that so that you do not come in direct contact with seed or the roots. Okay. It may be advantageous to employ 2 or more application methods or split the timing of applications or use 2 product types to increase the total amount of plant available nutrient throughout the growing season. Some photos of healthy plants on the left, the soybeans, versus sulfur deficient plants on the right. Here again, sulfur predominantly is not mobile within the plant, so therefore it does not store it and then relocate or translocate within the plant. So generally the deficiency symptoms will show in the new growth in the top of the plant, and the lower part of the plant will remain darker green. The best method to diagnose a sulfur deficiency is, I suggest, going using 2 methods: the plant tissue analysis in conjunction with the soil sample. With a plant tissue analysis, if you have a sulfur concentration that's 0.2 to 0.5%, you should have an ample supply of sulfur available. When doing the soil test for sulfur, there are a number of factors that compound this situation. You've got sulfur from organic matter and minerals. You've got sulfur being added from precipitation, that from the atmosphere as sulfur dioxide, and then sulfur that you add in manure and fertilizer amendments. All of these here again compound and is constantly changing. So I consider a soil sample strictly a snapshot in time, as that will be changing from day to day and from field to field. And also, when collecting those soil samples, take into consideration a number of factors: the topography, the soil type, your cropping history, areas where it may have received manure applications. All of these should be sampled separately or individually so that you can manage each area specifically. And then the area that I get the most resistance from soil sampling standpoint, with sulfur, we like to see soil samples collected from 0 down to 6 to 8 inches deep, and then retain that sample, then go back into that same opening and go from 8 inches down to 24 inches. Sulfur will leach out of the rooting zone and actually adhere to the higher clay concentration in the subsoil, and your deeper rooted crops such as corn will tap into that subsoil area later in the growing season. So a more accurate recommendation can be provided with soil samples collected at the second depth to give us a better idea of the availability of sulfur throughout the growing season. Now, when collecting plant tissue samples, be sure to collect the appropriate plant tissue. If you're working with seedlings, you're talking about the whole plant. Mature plants, you're working strictly with leaf and stems. In the case of soybeans, it's strictly the trifoliate leaf, most fully developed one. Just be sure that the plant you collect tissue samples from are at the same stage of growth, and then collect your soil samples and then request a complete analysis on both the soil samples as well as the plant tissue samples. Then another area that doesn't receive as much attention, and what I'd like to focus on from this point forward, is the soybean response to sulfur and its relationship to seed quality. And generally, seed quality is evaluated on the basis of both protein content and oil content. And in some cases, increased seed protein tends to reduce the oil content. And according to Kaiser and Kim, both of those factors are inversely related. Soybean seed protein content can be 35 to 40%, and then once the converted to soybean meal, which is an important animal feed protein additive, that can range in protein content from 46 to 50% protein. Methionine is one of the essential amino acids I referred to earlier that contains sulfur. It is important in plant metabolism. It's also a requirement for non-ruminant animals as far as balancing rations, and oftentimes that methionine content is too low for non-ruminant animals and has to be adjusted with a ration. Seed protein is influenced by individual effects of nitrogen and sulfur. Concentration is regulated by nitrogen availability, and this is one reason why we need healthy plants throughout the growing season. Healthy plants have a higher rate of nitrogen fixation that takes place, so we have a greater availability of nitrogen within that plant. And the availability of the sulfur amino acids in the seeds influence the production of the storage protein as well. So we need to maximize the amount of amino acid activity in those seeds later in the growing season. To evaluate soybean response is influenced by sulfur additions. Seed quality and seed yield tends to be more consistent than conventional soil fertility status. And based on some recent research, this is certainly a different perspective. In a research trial conducted by Hitsuda and others in 2014, he revealed that soybeans with a sulfur deficiency, those seeds contained less than 15.15% sulfur, whereas soybeans with sufficient sulfur nutrition, those seeds contain 0.23% sulfur. So here again, with the 0.2% sulfur being the critical level, once we got below that, we saw a protein content begin to decline significantly. Kaiser and Kim at the University of Minnesota in 2013 conducted some soybean research evaluating response to sulfur, and they concluded that the sulfur concentration at the V5, which using whole plants, and at R2, the trifoliate, the sulfur content, and the grain content of sulfur. So all these had a significant correlation to yield, and they concluded that the best factor correlating yield to response with sulfur was actually the grain sulfur content. So here again, going back to using that sulfur content in the grain, relating that to a soybean response. Interesting enough, soybean seeds tend to be low in methionine and cysteine, which are your two primary sulfur-containing amino acids, and this is naturally occurring. So to enhance seed protein and quality, we have to have greater rates of methionine synthesis within that seed. In order to increase that synthesis, we have to provide adequate plant available sulfur throughout the growing season, and resulting in higher levels of seed protein and oil content taking place. This is a results from a trial that H.G. Baker conducted over a 3-year period, evaluating our products and the release of sulfur. And as you can see, even after 12 weeks, I'm still seeing an increase in the release of the sulfate between the two products. So keep this graph in mind as we move forward. Looking at another graph from research conducted at the University of Illinois in partitioning the sulfur uptake for 60 bushel soybeans. And notice that the dark green area represents the leaves, the lighter green stem and petioles, the red being the flowers and the pods, and then the blue representing the sulfur that's in the soybeans. So on the y-axis we have sulfur uptake in pounds per acre. On the x-axis we have actually two readings for you, days after planting and then the growth stage of the soybeans. And then on the right side is the percent of uptake of sulfur by the different parts of the plant. And notice that by the time you reach R2, which is beginning reproductive stage, is when you start to see a rapid uptake of the sulfate, and continues to increase dramatically as you progress through the growing season. Okay. Now I would like to direct your attention to one area here. We've got approximately 60% of all the sulfur going to the seed. And earlier we mentioned that sulfate is not translocated within the soybean plant, and that's minimal. As you look at this, you notice this hump here and go straight across, and looking at approximately 25% is actually translocated out of the stems and the petioles and the flowers and the pods. And notice these are the plant parts that are closest to the seed. We have approximately 25% that's actually translocated to the seed. Then the remaining 35% of that sulfur then has to come through the plant root system later in the growing season. When I say later, we're talking about between the R6 and R8, which is at maturity. So that very late in the growing season, approximately 35% of the sulfur going into the seed during the latter part of the maturing process. In a research project found that the mobilization of sulfur from the vegetative tissue was actually greater than 30% when you had sulfur that was sufficient. And then in deficient sulfur conditions, less than 15% was actually translocated. So here again, influencing what I just described on the previous graph. And then sulfur uptake during that reproductive growth stage is being converted to seed protein through the amino acid synthesis process. Now what I'm about to show you on this graph is a trend. It's not specific. It's going to vary from field to field, soil type to soil type, farm to farm, and region to region. But it's a trend that I think most of us would anticipate occurring, and that is with most of your sulfate products. If you apply it pre-plant, once it dissolves in soil water, it becomes immediately available and has high availability in the early part of the growing season prior to the high demand for the crop going mid to late season. Whereas you're using the sulfur bentonite products, we have a gradual increase throughout the growing season going into the later season when that crop is maturing and that 35% or so of the protein and sulfur being generated in that seed, being an important part of the management of the sulfur products that we're applying. This is a trial from last year, and I don't like to use 1 year, one location, but certainly provides a positive indication of what can happen looking at the addition of sulfur and its extension into the later part of the growing season and the amount of seed protein that we experienced. And with an untreated check at 34.7% protein, whereas with a couple of our products we saw increase of 1% in protein, although it does not sound great, but when you add 1%, that can be significant when you're converting that to a protein supplement for livestock. Here's the yield response for another trial that we conducted in the Mississippi Delta region. This is the average over 2 years of 12 strip trials over a north to south about 100-mile range and east to west about 50-mile range over 2 years. And notice that we received between the control and two of our products of 8 bushel yield increase in the soybeans, and which is obviously a significant response as compared to some of the other products. So here again, managing and having a full season availability of sulfur certainly enhance the potential crop response. So optimizing soybean production with attention to details, fine-tuning your management decisions, and employing the 4R best management practices to maximize crop benefit from added nutrients certainly can contribute to maximizing yield potential and seed quality. So with that, I'd like to summarize the presentation. Here again, sulfur is an essential nutrient for plant growth. Plant sulfur deficiencies are more prevalent, and enhancing soybean seed quality can be critical to production management going into the future. A number of factors influence sulfur availability, especially from the elemental sulfur standpoint, that being soil type, sulfur particle size, soil temperature, microorganism population, and soil moisture. And then a planned sulfur nutrient management program provides a more consistent sulfate availability throughout the growing season and from year to year. So with that, there are a number of products that our company offers for soybean production, and actually direct your attention to our website if you further information. And we also have an app available for calculating rates that are needed, along with image library, and that's available through the App Store for the iPhone as well as Google Play for the Android versions as well. So on behalf of H.J. Baker and the Illinois Soybean Association, Daniel, I like to take this opportunity to share this soil fertility information that may contribute to producers' knowledge base, leading to more informed management decisions. So we appreciate the cooperation with the Illinois Soybean Association. So with that, I will turn the program over to you, Daniel.
Okay, Russ, thank you very much. Russ, can you back up to that crude protein slide? Again, just go backwards. The crude protein.
Crude protein.
That one. No, next one. The next one forward. Go in the other direction. Go forward. Keep going forward. One more. Nope, not quite. Keep going. Oh, there we go.
That one?
That one. I have a question here. Okay. You talked about this raising this percent crude protein, raising it 1%. That's a very important number, 1%, 1 or 2%, because the crude proteins are trending downward. But if we could get back to like this 35.5% crude protein in the beans, like you show here, that puts us right at a certain spec. So it takes about a 35% soybean, crude protein in a soybean, to make a 47.5% crude protein in meal. That is what the market wants and what the processors, the crushers, are selling. They try to sell for 47.5% crude protein, but oftentimes they can't quite meet that because the protein in soybeans has been trending downward. So I just want to point out this 1% increase is actually quite huge. When it comes to increasing crude protein in soybeans or in wheat, we're only talking about a percent or two, right? We're not trying to increase it 5%, just a little bit to keep it in the market. So that increase, like from 34.7 to 35.6, 35.7, that's actually quite significant, because we just bumped up that crude protein just a percent or so. For most of the soybean producing regions in the U.S., that's all we need. If you reach out into more of the further northwest corn belt of Dakotas, northwest Iowa, western Minnesota, well, they need a several percent to draw several percent more crude protein. But sulfur might play a role here. I have a question here. On this, you talked about these. Were these products put on at planting, or were they top dressed?
prior to planting and incorporated.
Right, prior to planting, and we saw from the previous graph where you had that line about that slow release, providing that sulfur through the season. In that graph from Fred Guido, you know, the plant, because it can't really remobilize sulfur right there, it can't remobilize the sulfur, you need that later supply.
Most definitely.
My question here is, you're thinking about soybeans and that sulfur needing that crude protein. If someone was trying to top dress sulfur on soybeans, when would be the best time to do that? If you were to do some kind of application of sulfur, like people want to do with nitrogen, would there be a window, a stage you should do that at?
I'm not sure I have enough research to give a specific answer to that, but my anticipation would be if you're using your sulfur bentonite products, you need to do that at planting or just right after planting in a no-till situation. If you're using the sulfate products, you can wait and go in top dress a little later because it's going to be water soluble and become plant available quicker. But here again, that's all a function of individual management criteria.
Correct. Let's get on to some other questions here. We have several. And it goes back, if someone applies 300 or 400 pounds of gypsum in the fall, would there still be a benefit from the benefit of sulfur to the soybeans next season? So if you look at, that's about, if you apply 400 pounds, about 20% sulfur, you're getting roughly about 80, if you apply 400 pounds, let's say 20% sulfur roughly, on that 400 pounds, that's around 80 pounds. If you apply that much gypsum in the fall, will it still be around the next spring, the next summer?
That depends. And here again, depends on how early in the fall you apply it. Here again, the sulfur or gypsum or calcium sulfate is not as water soluble as your potassium sulfate or ammonium sulfate, but it will react with water in release somewhat faster than the bentonite products. So here again, it depends on how much sulfate has been converted in the fall and going through the winter and the amount of rainfall and the snow and the leaching that takes place. It's difficult to say. There should be enough there, but there again, I'm not going to say all of it's going to be there. That's for sure.
Okay. If you put on, we're going to use Ohio for an example, where you're at, rest and the rainfall patterns you experience. If you put on 40 pounds of sulfate, let's say in the fall, what percent of that will be leached by the time sulfur uptake begins?
For
normal rainfall,
soybeans, I would not recommend putting ammonium sulfate on in the fall because it's going to immediately dissolve, and that sulfate is going to be leachable for the duration of the winter months, and you're going to lose a good portion of that before you get to the crop planting time.
So not in the fall at all. Okay, that's not, because it's going to leach. Okay. Another question: if I apply my element of sulfur in the spring of 2016, that's the spring of 2016. How much of that product is going to be available for the 16 soybean crop? So I'm thinking they're asking, if you apply 50 pounds, will 100% of that be available in the summertime? 80%? Because even though it's a slow release, what percent of that product will be available in season, that first season?
Daniel, that's a question I get almost daily, and I cannot give a specific answer. There's a number of factors come into play. I talked about a number of those during the presentation, that being the crop you're working with, the soil type, temperature, amount of moisture, all those factors come into play as to influencing the rate of release. And here here again, it also is a factor, is influenced by, is this the first time you've applied a sulfur bentonite product in your field? If it is, the natural occurring bacteria that converts the elemental sulfur to sulfate is going to be low, so that initial response is going to be slower. Once you've got that population sulfation build up in the consecutive years, then that reaction is going to be much faster. So here again, I'm going to not venture out to say, give you a specific number of release and the percentage of it. No, it will not be 100% the first year. So there will be some carryover from that, because once a bacteria become active, they do not convert all that sulfate at one time. It's gradual going forward.
So that's an important point. I had never realized before that, because you're right, you have to have, if you haven't applied an element of sulfur, that population of bacillus won't be very large, so it has to build up.
Correct.
That's each year, so it won't convert as fast. That's a very important point I had never thought of before. So regardless if it's the first application or second application, there's always going to be some carryover to the following year.
We have found that in our research. Yes, if you say instead of, normally if you apply, say, 30 pounds of sulfur on an annual basis, you can apply 100 pounds and skip the next 2 years and still have enough carryover for the next 2 crops. And our research has shown some positive responses in doing that.
That was exactly my next question. Could you put out an application, like, for example, with lime, that will carry you 3 years and cover the needs of 3 crops? So that's a good strategy.
Yes.
Cool. So here's a kind of a very innocuous technical question. If someone applies 35 to 40 kinds of elemental sulfur, considering that it's the process of converting it to sulfates acidifying, do you know how many pounds of lime will take to compensate for that? You know, people have done the math with nitrogen, right? You apply nitrogen, you might have to have so much lime to compensate for that nitrification.
Right, right.
Oh, do you know what the number is for elemental sulfur?
Yeah, it would be about 3 to 4 pounds to 1, if I remember right.
Okay, 3 to 4 pounds of lime per 1 pound of elemental sulfur. Is that correct? That's what you recall?
That's what I recall, but I would not say 100% on that.
Okay.
And that's going to be a function of the soils as well and the buffering capacity to adjust that change.
Mm-hmm. When people are making, sulfur recommendations, and growers realize and agronomists that sulfur deposition is going down, and so they got to apply sulfur. Can they take a credit for sulfur from the previous crop? Can one reliably do that?
We have not recommended that. I've not seen any research from universities suggesting that. Just don't have a good correlation of data that consistently relates to the amount of decomposition and release as it relates to the crop. For example, with the nitrogen credit we offer soybeans, there's significantly more research data that correlates back to the amount of nitrogen that's released from soybean decomposition of the residue as compared to the sulfur. So I don't have any specifics on that, and generally suggest farmers to look at the crop nutrients uptake more so than the removal to account for sufficient amount of sulfur for individual crops.
Okay. So a couple more questions here.
Okay.
Can people apply sulfur foliarly? If you're putting like some thiol or something, can you apply a foliar sulfur form to the leaf? Will that have an impact versus like pre-plant or top dress?
Not that I'm aware of. I've not done any research, not seen any research that's done with foliar application. There's the form that the plants actually take up through the foliage is a gaseous form of sulfur dioxide. So I would focus on applying sulfur to the soil as a soil addition.
Okay. Okay. One question here. We talked about the tissue concentrations, and you said like 0.2 to 0.5%. Was there a differential between like oilseed crops like soybeans and grain crops like corn? That percent in the tissue concentration, are they the same, or is there a differential?
Oilseed crops, soybeans falls in that same category, but doesn't have quite as high demand as, say, a canola does. Canola has a much higher demand, so that would be higher. It's more like the 0.25, if I recall correctly. Soybeans, 0.2 is sufficient for the sulfur concentration in the plant. But once you get below that 0.2, then things start to decline.
So that if you look at some of these nutrient concentrations for crops, there will be some differential in that 0.2, 0.25 or something for different crops.
Yes,
okay,
most definitely.
Okay. In relation to your target products, how are these products applied alone? Can they be combined? What are the different options for applying your target products?
You can apply those alone. If you can adjust your spreader to apply low rates, we generally recommend to blend that with your phosphate and potash products or dry nitrogen products. The bulk density is about 76 to 80 pounds, depending on which product you're working with. So the density is very high. It's actually higher than potash, so you get a good spread pattern and distribution within the spread pattern. So generally we recommend blending that. From a crop nutrient standpoint, you only need 20 to 35 pounds of sulfur applied. So adjusting that spreader to that low rate is very difficult, unless you decide to put on enough for, say, 3 crops and put on 100 pounds to the acre, then it can be applied alone if you can adjust your spreader down to that 100-pound rate and get a consistent distribution pattern.
There's one thing I think goes back to your slide when you're looking at uptake of sulfur in soybeans from that one slide from Fred Below. That sulfur has to be pretty much available in the soil all year long, pretty much because it's not mobile.
Correct.
It has to be available the whole season.
Yes. In the plant available form, the whole season.
Okay. Well, that gets to our questions. I think we're about done. You got through that faster than I thought, considering the number of slides you had. So a very good job on that.
Well, thank you.
Just take a moment first. I want to thank Wesley Haun for his presentation today. We're just about done. Again, as a reminder, as a CCA, that if you registered and put in your CCA number, this will be applied. You will receive a credit for attending today. If you're listening to the recording of this event online, just a reminder, you have to go back online, log into your CCA account, and self-apply for a credit for this one event. I want to thank everyone for listening and participating today and for the questions you submitted. And on behalf of the Illinois Soybean Association and our sponsor, H.J. Baker, for sponsoring today's webinar, thank you all for attending, and have a very good spring.